Okay, now we're into tutorial 1 part 2, wherein we deal with 2 planes and 3 planes. For question 1 part 1 of tutorial 1 part 2, you are given the equation of 2 planes and you're interested in 2 things. Firstly, to find the angle between the 2 planes. To find the angle between the 2 planes, a cosine theta equals to 9 minus 3 minus 4 dot with 2 minus 1 minus 1 divided by, now to find the cosine between the 2 planes, which is the same as the cosine between the 2 normal vectors, you will always need to divide by the magnitude of the 2 vectors. It's actually a dot product. So I'll find the magnitude of the vector 9 minus 3 minus 4. It gives me 106. Right, it gives me 106. Let me check one again. 81 plus 9 plus 16. Okay, 106. Indeed, this is 106, and this is 6. Right. But to find the angle between 2 planes, you must always make sure that it turns out to be an acute angle. So you need the modulus on the numerator. So now let's do the arithmetic. For the numerator, you have 18 plus 7. 18 plus 7 is 25. So this gives me 25 over 106 over 6. Then you can use a calculator. For this case, you will obviously need a calculator to do it. Okay, taking a calculator, I'm going to calculate this in degrees, right? Inverse cosine 2.5. Okay, I'll get an angle of, from here, right? I'll get angle theta as equals to 7.557 degrees, or you can say that theta. Okay, let's round off. It's approximately 7.6 degrees. Right, this is how you can find the angle between 2 planes. Right. So bear in mind, you must always put a modulus. Just make sure that the angle will turn out to be an acute angle. Then the next thing is, you want to find the line of intersection between the 2 planes. To find the intersecting line between 2 planes, one method that we learned in the lesson is to start off with the Cartesian equation of 9x minus 3y minus 4z equals to 7, and then 2x minus y minus z is equals to 1. These are the 2 equations of the 2 planes. What we are going to do is, we are going to rewrite this by letting z to be equals to lambda. So then this gives you 9x minus 3y equals to 7 plus 4 lambda. Then this gives you 2x minus y equals to 1 plus lambda. So what we've done here is, we have just simply replaced z as lambda, and then we now have 2 equations in x and y that we intend to solve for x and y in terms of lambda. So now solving these 2 equations, let's see again, to solve this 2 equation, times 3, I get 6. So x is equals to times 3, 7 minus 3 is 4 third. Times 3 is 12. Okay, times 3 I get 4 minus 3 is 1 plus lambda over 3. But I get this for my x. And then I gotta find my y. Y is equals to this again, that's the arithmetic. I'm going to plug this thing inside here to find my y. So it's going to be 5 over 3 5 over 3, and then this is 2 minus lambda over 3. Okay, so if I solve that simultaneously, I got this value for x and y in terms of lambda. Right, these are all in terms of lambda, and then I'm ready to actually write down the equation of the intersecting line. My intersecting line will be equals to 4/3, 5/3, and then 0 plus lambda of 1/3 minus 1/3 and then 1. Okay, let me tell you where I get this number from again. After I've solved for x and y in terms of lambda, to write down the equation of the line, I'll put x, y, z in this form. The x will be 4/3 plus 1/3 lambda. You can see 4/3 plus 1/3 lambda is here. 4/3 plus 1/3 lambda for x. For y is 5/3 minus 1/3 lambda, and for z is just lambda. So this is your equation of the line of intersection between the two planes. Now the solution that you have in your answer key, and this may not be the same, but I want to help you out a bit. I want to write down for you what is in the answer key. The answer key is r equals to 0, 3 minus 4 plus lambda of 1 minus 1, 3. Even if the answers are not the same, I like you to learn a way to check that they are equivalent. Okay, first and foremost, to say that these two lines are the same line, first and foremost, you want to check the directional vector. So you check, is this vector parallel to this vector? It's true, right? Because this vector is 3 times of this vector. So therefore, I know that these two lines, at the very least, they are parallel. Then how do I know that these two lines are actually indeed the same line? I just need to check that this point on this line can be obtained from this equation by, in this case again, to obtain this point in this equation, I look at these two and I say that if I put my lambda as minus 4, if I put my lambda as minus 4, right? 4/3 minus 4/3 will be 0. Put lambda as minus 4, right? So I'm going to get what? I'm going to get 5 minus 4 times 1 become plus 4. So it's 5 plus 4, 9. 9 divided by 3 is 3. Lambda times minus 4 gives me minus 4. So therefore, it is true that these two lines are actually the same line, although they look different, right? So both are acceptable. Okay, next one, the same thing goes. You are asked to find the angle between the two lines. Once again, to find the angle between two lines is to find the angle between the two directional vectors, except that you need the modulus on the numerator. The modulus, again, is needed on the numerator to make sure that you get an acute angle. And this gives you 14/3. This you need a modulus. So your cos theta turns out to be minus 3 minus 2 minus 5 minus 4 is 4. And then you take out a calculator to calculate the value of theta. Okay, let me take a calculator out. So this gives me, I'm actually calculating now, I'm not relying on answer key. I get a value of 51.887 degrees or 51.9 degrees. Okay, that tallies with answer key. Then next thing is, same thing, we now want to find the intersecting line between these two planes. For this part 2, I intend to find the intersecting line between the two planes in another fashion. Remember, we have a second method to find the intersecting line. All line has two vectors. And if you recall, to obtain the second vector, right? To obtain this vector, all we do is we take the normal of the first plane, cross product with the normal of the second plane. So let's perform the cross product. Cover the first row, 3 minus 2, cover, minus 1, minus 2, minus 3, middle row need a minus, 1 plus 3 is 4. Right? Take 1, 3, 4. Now I want to find the point on the line. So we learned that for such a thing, we can arbitrarily give 0 as a first entry, and then you have B and C to be found. How do you find B and C? If this point is the line of intersection of the two planes, this point must lie on the first plane, and this point must also lie on the second plane. So I put this point into the equation of the first plane. I'll get minus 3b plus 2c equals to minus 4. I put this in the second plane. I get b minus c is equals to 1. So from here, I want to solve for b and c simultaneously. So to solve them simultaneously, I'm going to have, if I times 3 to this, times 3 to this again, times 3 to this, add up together, this gives minus c, times 3 together, add up together is minus 1, so c is going to be 1, and b is equals to b, it's going to be 2. Let's check again, minus 6 plus 2, yeah, indeed. So I get b and c to be 2 and 1. So therefore, the line of intersection turns out to be 0, 2, 1, plus lambda of 1, 3, 4. I hope you can see on the video. Yes, just nice. Right, and that completes question number 1, part 1 and part 2. Now into question 2 of tutorial 1, part 2. In this question, we are given two planes. We are given two planes, pi 1 and pi 2. And now in this case, we want to check firstly that this point A actually lies on both planes. How do you check that this point A lies on both planes? It's very simple, right? Put this point into the left hand side. 2, 3 minus 2. Check 2, 3 minus 2. If you have to check it, 2, 3 minus 2, you dot with 3 minus 2 minus 2. What do you get? You get 6 minus 6 plus 4. So you get 4. It tallies. Right? It tallies with the equation of the first plane. You see? So this implies that A lies in pi 1. Okay? A lies, let me write more carefully. That A lies in pi 1. A lies in pi 1. Then you do the same thing, You take the point A, take this point A, dot with 1, 3, 1. 2, 3 minus 2, dot with 1, 3, 1. What do you get? You get 2 plus 9 minus 2 gives you 9. So therefore, A lies in pi 2. So if you have that A lies in both planes, therefore A will also lie in the intersecting line of the two planes. So that to find the intersecting line of the two planes, I now can say that the first vector is obviously 2, 3 minus 2. And then to find the directional vector of the intersecting line, what I can do is, remember in the earlier question 1 part 2, to find the directional vector of the intersecting line, I could just do this by taking the cross product of the two normal vectors. Just cross product these two normal vectors, it will give you the directional vector of the line. So how do you cross product? Cover the first row, minus 2 plus 6 is 4. Cover the second row, 3, 5, ending a minus. Cover third row, 11. So this is how you can actually obtain the directional vector of the required line. Now moving on to question 3. in question 3, you are given the equation of two planes, and it requires you to do the same thing, which is to find the intersecting line between the two planes. However, what's different here is the equation of two planes are given to you in this other form, the parametric form. So of course, in the parametric form, you can say I could potentially convert this into the dot product form, convert this into the dot product form, and then I can find the intersecting line between the two planes, like what I have been doing all the time. However, you can choose not to do this, which I'm going to do in this question. I intend to just use whatever is given to me, these equations, and using this equation, I want to solve for the line of intersection between the two planes. Just like solving for any kind of intersection, to find the intersection between two planes, the basic idea is to try to solve them simultaneously. So look here, I intend to solve these two equations simultaneously by equating this whole thing to this whole thing. Yep, make no mistake about it, I intend to form three equations, and there are a lot of numbers involved, and I intend to form these equations brute forcely, no shortcut, no. So what I'm going to do is, I now intend to equate these two equations, this equals this, and form the three equations, and I'm going to shuffle terms around, and my three equations will be 0, 0 lambda plus mu minus 2s minus t is equals to minus 2. This is my first equation. My second equation is minus lambda minus mu plus s minus 0t equals to 1. And my third equation is minus lambda minus mu minus 0s plus t equals to minus 1. So I have actually simply equated the two equations. I shift terms around and I obtain these three equations in 4 unknowns. After having written down the three equations, what do you think you want to do from here? What's going to happen here is, from these three equations, which is in terms of 4 unknowns, I intend to actually try to establish a relationship between lambda and mu, or s and t. The whole idea here is, from this equation, I intend to establish a relationship between lambda and mu. If I'm able to write down mu in terms of lambda, by plugging into here, I can collapse this into an equation of a line, and this line then serves as the line of intersection between the two planes. Likewise, if I can find t in terms of s, I can do the same thing. I can replace the t in terms of s, and then reduce this whole equation into an equation of a line, and it will be the same line of intersection between the two planes. Right, so my aim right now here is to try to establish either this or this game, a relationship between lambda and mu, or a relationship between s and t. And how am I going to do it? Okay, you want to note that in equation 2, right? I can see that s is equals to 1 plus lambda plus mu. So I'm going to write down, okay? From equation 2, the s is equals to 1 plus lambda plus mu. And then from 3, t is equals to minus 1 plus lambda plus mu. So now that I got s and t in terms of lambda and mu, I intend to plug these two into here and here, so that I am going to get mu, there's no lambda, right? 0 lambda. Mu minus twice of this, minus 2 lambda minus 2 mu, then minus t plus 1 minus lambda minus mu is equals to minus 2. So what I've done here is, from these two equations, So from these two expressions for s and t, I put into 1 to get this line. So from this line, I'm going to tidy things out a little bit. I got mu gone, got minus 2 mu. So I can say that this minus 2 be gone. So I got minus 3 lambda minus 2 mu plus 1 is equal to 0. Let me check it that I'm correct first. Let me check. This 2 will be gone. You got minus 2 mu, minus 2 lambda, minus 3 lambda. This 2 will be gone plus 1. Okay, so I should get this. Okay, so from here I can actually say that mu is equals to half of 1 plus 3 lambda. Okay, I can now say that mu is equal to half plus 3 lambda. So what's going to happen next is I intend to put this into here. Then I can produce an equation of a line from there. Okay, so I need some space. I'm going to erase off here. So while I'm erasing, you want to try to plug it in and work out the arithmetic. Okay. So now we are ready to actually plug this inside the equation of the first plane. Alright, and from there we intend to reduce it into an equation of line. But before that, let me check that my calculation is correct first. I want to make sure. Okay, I think I made a slight mistake here. This should be a minus 3 lambda. Okay, so it's always good to check along the way, if not, otherwise your mistakes will just cascade down. So now I'm ready, you must be very brave to just plug it in, put this thing inside here. So now I intend to plug it in. I will get R equals to 210 plus lambda 0 minus 1 minus 1. In place of mu, I put in as half of 1 minus 3 lambda, and then the vector 1 minus 1 minus 1. Okay, now how do I tidy up my equation? Okay, look, don't blink your eyes, don't blink your eyes. Okay, right, so what I'm going to do here is 210 will plus half times 1 times this vector. So we come 210 plus half minus half minus half. 210 plus half minus half minus half. So 210 plus half is 5 over 2. 210, the 1 minus a half gives you a half. And then 0 minus half is a minus half. Alright, that's my first vector. Then for the lambda, if I take out lambda from here and here, right, I'm going to get 0 minus 1 minus 1 goes with minus 3 over 2 times this vector. Right, this one will go with minus 3 over 2 times this. So I will have 0 minus 3 over 2 times 1 will just give you minus 3 over 2. Then minus 1 plus 3 over 2 will give you half. And then minus 1 plus 3 over 2 will give you half again. Right. So this becomes an equation of a line. Okay, and let's see again the answer key. the answer key gives you an answer which is okay, the answer key given to us is r equals to 4, 0, minus 1 plus lambda of 3 minus 1 minus 1, right? So let's see whether or not we match the answer key. As I said, equation of line may not be unique, but we have a way to actually check if they are equivalent. This is 3 minus 1 minus 1, it is parallel to this vector, right? Because if I times minus 2 to this, I will get this vector. So these two vectors are parallel, so it's good. Next thing is, can I get this point from this line? If I put lambda as minus 1, this minus 1 times this will give me 4. If I put lambda as minus 1, this will give me 0. If I put lambda as minus 1, I get minus 1. Yes, so therefore, these two equations are equation of the same line. So this is actually the equation that tallies with the answer key. This is the equation of the intersecting line between the two planes in 3 part 1. So I want you to understand what is going on, that having obtained these three equations, the aim is to try to establish a relationship between mu and lambda, or t and s. You could potentially have gone about doing it so that you can establish t in terms of s, and likewise replace the t in terms of s and tidy up this equation. You will find that you will get an equivalent equation of the same line, right? And that is question 3 part 1. In tutorial 1 part 2 question 3, we are on question 3 part 2. In question 3 part 2, right, you're given two equations. Now it's a parametric and dot product, right? So again, we want to find the intersecting line between these two planes. Like I said before, you could have, if you wish to, convert this also into a dot product form, and then you do the same thing all over again. But just like in the 3 part 1, we want to keep the equation as they are and use these equations to solve for the intersecting line. Let me ask you this question. How do you think this question can be done? Okay, just like in 3 part 1, the idea here is in trying to solve these two simultaneously for the intersecting line, the idea here in this question is we will try to do the same thing, and that is we will try to establish a relationship between lambda and mu. And how do we go about this? To solve these two simultaneously, what I'm going to do is I'm going to do this solving simultaneously. What I'm going to do is I am going to put this entire thing into the R here, and I perform the dot product. So what I'm saying here is I'm doing this. I know it's quite a fair bit to do, but we're going to do it anyway. 0 minus lambda 1 plus 2 lambda dot with 2 minus 1, 6 equals to 5. Okay, so we just plug it in, hoping to establish a relationship between lambda and mu. So to do this calculation, what I have here is 6 plus 1, 7. Bring over the 7, 5 minus 7, you get a minus 2. Right? Then next thing is this times this 4 lambda plus 6 lambda, 10 lambda plus 2 lambda is 12 lambda. And then you have 4 mu minus 18 mu is minus 14 mu. plus 2 mu is minus 12 mu. Minus 12 mu. Okay, so there you are. What you have here is mu is equals to lambda plus 1 over 6. Okay, let me check my calculation first again. Maybe I should check that I copied the equation correctly. 3, 0, 1, 2, minus 1, 2, 2, 3, 2. Okay, 2 minus 6. Oops, I think I made a mistake. I made a mistake because this is not 5. You see, it's always good to check, this is actually minus 5. And then this is actually minus 12. And this is therefore plus 1. See, luckily I checked. Okay, so my mu is equals to lambda plus 1. So then from here, right, I'm going to put my mu in like what I did earlier on. This r equals to 301 plus lambda 2 minus 1, 2 plus lambda plus 1, 2, 3, 2. Now we have to perform the simple arithmetic here. I'm going to tidy up this one as r equals to, okay, let's see, 301 plus 1 times this becomes 3 plus 2 is 5, 0 plus 3 is 3, 1 plus 1 times 2 is 3. And then for lambda portion, right? Lambda of this plus lambda of this becomes lambda of this plus this. 2 plus 2 is 4. This and this gives you 2, and lastly 4. Okay, so my answer that I have is this. Let's check against the answer key. The answer key given to you is r equals to, this answer key, the green color is answer key. Two, 1, 2. Okay, so just to confirm that my answer tallies with the answer key, let's check again. These two vectors are parallel to each other, so therefore it's okay. So next is you ask, can this point be found on this line? So because I need a 0, right? That suggests to me that if I put my lambda as minus 3 over 2, let's see again. If I put my lambda as minus 3 over 2 into here, this will make this one 0. This and this, right? This and this with a 5. 5 minus 3 over 2 times 4 gives you 5 minus 6, and it's minus 1 is true. Okay, it's true. So 3, and then put lambda as minus 3 over 2 times 4. 3 minus 3 over 2 times 4 is 3 minus 6, so it's minus 3. So therefore, these two equations are actually equivalent. And that completes question 3, part 2. Okay, in tutorial 1, part 2, you are still in tutorial 1, part 2, now is in question 4, part 1. You are given 3 equations of 3 planes. How do we manage 3 equations in a question? If you can recall, the first thing that we want to do is to check if there are parallel planes among them. So how do you check? You check the normal vectors. The first normal vector is 3, 2, 1. Next one is 2, minus 1, 3. Next one is 1, 1, 2. It is not too hard for you to see that none of them is parallel to any other. So therefore, the figure 3, which is 3 parallel planes, and the figure 4, which is the case of 2 parallel planes, they are out. So the next thing is, to go on from here is, we want to first and foremost manage the first 2 equations first. Given that these 2 equations are non-parallel, they will surely meet along a line. So the thing is, we want to find therefore the equation of the intersecting line. How do we do it? Do you remember? There are two ways about it. The second method that we learned was this, no? R equals to plus this, remember? So we can obtain this second equation, which is the vector parallel to the line by taking the cross product of the two vectors 3, 2, 1 cross with 2, minus 1, 3. So how do you perform the cross product again? I'm sure you know by now. So if I were to do a cross product, I am going to get 7 minus 7 minus 7, right? I'll get this as my direction vector on the line. Then next thing is, as you already know, we can just guess it, that maybe let's try it again. Maybe the third value, the z component is 0, right? Arbitrarily, I have decided to put 0 in the third component, right? Previously in the notes, I have put 0 as the first component. It really doesn't matter. So if you think that there's a point A 0 on the plane, so from here I plug it in the equation, I get 3A (2A). So from these two, you want to solve for your A and B. To solve for A and B, you got 35. So A is 5. I think A is 5. And then B is equals to 0. Okay, B is equals to 0. Okay, so I get this number. So therefore, the equation of the line that I have here is R is equals to 5, 0, 0 plus. Okay, let me change it. Okay, I don't want to deal with big numbers. I deal with small numbers. Okay, I can always change the direction vector. So if you remember, the first thing that we do in dealing with three planes is to manage the first two planes first. Look for the intersecting line of the first two planes. And now the next thing is we want to study the relationship between this line and this plane. So let me call this line L. Let me call this line L. Remember, we always call this line L. Let me call this third plane pi 3. So now you want to study the relationship between the third plane and the line L. So what you do is, you want to first and foremost check that the line, in this case, right, in this case, it is not parallel to pi 3, In this case, you want to check, this plane and this line are not parallel. Why are they not parallel? Because 1, 1, 2 dot with 1 minus 1 minus 1 is not 0. Right? You can do a calculation to check it's not 0. So if the line L is not parallel to pi 3, that means the diagram will look like this. So they will surely meet at a point. They will surely meet at the point here. So now you want to solve for the intersecting point between the line L and the plane. So what you do is, you want to put this whole equation, this entire equation, right, into the equation of plane. Pi 3, pi 3 has an equation that looks like this. 1, 1, 2. So in place of R, you're going to bring as 5 plus lambda dot with 1, 1, 2 equals to 7. And then upon doing so, let's see again. Okay, 5, 2, 5 is 2, so lambda is supposed to be -1. Okay, you check my calculation. Okay, I really do it on the spot. Let me check again whether I'm right. Okay, -2. This is +2. So my lambda is -2. Therefore, this line meets this plane at this point, and this point is what? This point is put lambda as -1. This point would be 4, 1, 1. So if this line meets this third plane at this point, 4, 1, 1, therefore the three planes meet at this point too. Right. So in this case, right, for part 1, you have the case where the three planes meet at a point. So correspondingly, based on the diagram in your notes, this corresponds to the case of figure 1 in your notes. In your notes, you refer to page 137, right? There's a figure there. There are 5 figures. Figure 1 is the case where the three planes actually meet at a point. So that completes for part 1. And now we are into question 4, part 2. Like all other questions involving three planes, the first thing we want to do is to check, are there parallel planes? And you want to observe very carefully that in this question, the second plane, right? The second plane, this is the second plane, and this is the third plane. You find that the second plane and the third plane, they are parallel, right? They are parallel. This is 2 minus 4, 2 is a multiple of 1 minus 2, 1. So pi 2 and pi 3 are parallel, but not for the first plane. The first plane has a normal vector that is not parallel to this, nor this. So therefore, you can imagine a scenario in this case, right, that look like this. The second, and then the third plane, and then the first plane is like this. And this is the case of what? This is the case of figure 4 in your notes. In your notes, page 137. Right? So this is the case where there are two parallel planes, and these two parallel planes, right, they are not incident planes, you know. These two planes are distinct, because if we divide through by 2, this is 1 minus 2, 1, but this is going to be 7.5, which is different from 8. So that tells me that plane 2 and plane 3, they are just parallel, and they are not incident planes at all. So in this case, right, because it is figure 4, they don't meet. The planes don't intersect. Right? Okay, that is for part 2. Let's look at question 4, part 3. Again, you are given 3 planes. Can you try to detect if there are parallel planes? Are there parallel planes among them? So there are no parallel planes among them. Okay, let's look at in that case, let's look at 4 part 3. Okay, in the case of 4 part 3, because they have no parallel planes. Okay, now let us look at 4 part 3. Again, you have 3 planes. You check very carefully that in these 3 equations of the 3 planes, they do not have any parallel planes at all. You can check the first with the second, the first with the third, and then the second plane with the third plane. So you don't have any parallel planes at all. So figure 3 and 4 are out. So now the same thing goes. We want to actually look for the intersecting line between the first two planes. To find the intersecting line between the first two planes, what you need to do is to solve the equation again. We have been doing that again and again. I hope by now you are familiar with the steps. So what we're going to do is we're going to rewrite this thing as 2x plus y equals to minus 2 lambda. So I'm doing the first method. 6x plus 5y equals to 6 plus 2 lambda. So we are letting your z to be lambda, so that my two equations are obtained by moving the z to the right hand side, and replacing z as lambda. Now from here, we want to solve for x and y in terms of lambda. My y is going to be okay, let me solve it from here. 3 it's going to be 6. Let me see again. 2 plus 6, 8, 4 lambda. I get this. Okay, let me revise again. That I now have found that y is 6 plus 4 lambda. Let me double check again. 12 minus 6, 8. Okay, so I think my y is 6 plus 4 lambda. Then my x will be equals to minus 4 minus 3 lambda. Okay, let me just be sure first, okay? Minus 24 plus 33 minus 18. Yeah, I think it should be correct. Okay, so therefore, based on this, the intersecting line between the first two planes ought to be like this. Minus 4, 6, 0 plus lambda of minus 3, 4, 1. So now, having found the intersecting line between the first two planes, we want to study the relationship between the third plane and this intersecting line. So what do you do first? We want to check, are they parallel? So let's check again. And we found that the line L is actually parallel to pi 3 because of what? Because if you take the normal vector of the third plane, you dot product with the direction vector of the line, you actually get 0. So therefore, I know that the line L is parallel to the third plane. So next thing that I do is I check, is this point on the line also on the plane? Let's check again. So you take minus 4, 6, 0, you dot with 1, 1, minus 1. You take this point, you dot product with the normal vector and check whether or not it's 4. So this gives me 2, which is not 4. So this point, right? This point, minus 4, 6, 0 is not in the third plane. So if that's the case, which means the intersecting line of the first two planes does not meet the third plane. So hence the three planes don't meet. Right? Given that mutually the planes are not parallel and they don't meet, Therefore, this is the case where the diagram look like this, and this is labeled as figure 5 in your notes. And this is the case where we call this the infinite triangular prism, right? Infinite triangular prism. That completes question 4, part 3. Now into question 4, part 4. Again, your 3 planes. You check they are non-parallel. So because they are non-parallel, you do the same thing again. Find the intersecting line between these two. Okay, the intersecting line. It comprises 2 vectors. Okay, and then you are already familiar by now that to find the second vector, right, is the cross product of 2 minus 1 with 2 minus 2, 1, right? So let's perform the cross product. 2 minus 2 is 0. 2 minus 2 is 4, it's minus 4. And then minus 4 minus 4 minus 8. Let's check it. 8, 0. Minus 8, 8, 0. Okay, right. Then you need the first point. How to get the first point? Like what we did just now, we can just simply, arbitrarily, we just think that the last point is 0. The last component rather, okay? So you can just imagine that this line has a point A, B, 0, right? So then I will have 2A plus 2B equals to 2, and then 2A minus 2B is also equals to 2. So that being the case, A equals 1, my A equals 1, and B is equals to 0. Right, if we solve them simultaneously. So therefore my line L, the line L will therefore be 1, 0, 0 plus lambda of, okay, let's use smaller number, right? Remember, I like to use a smaller number. Instead of 0, minus 4, and minus 8, I prefer to just use 0, 1, 2. Okay, now that we have the line L, we want to check how it interacts with the third plane. So first and foremost, you want to check. What do you check? Let's check whether this is true or not. How do we check this is true? So let's perform this. 8 minus 6, 3, dot product with 0, 1, 2. This equals 0 because the dot product of the normal vector and this directional vector of the line, because this dot product is 0, therefore the line and the plane are parallel. Okay, so so line L is now parallel to pi 3. The next thing we want to check is this point on the line L also on the third plane? So how do you check? So you do 1, 0, 0 dot with the normal vector of the plane, and this is equal to 8. So this implies that 1, 0, 0, the point on the line, lies in pi 3. So when that happens, it means the entire line, so by 1 and 2, right? By 1 and 2, line L lies in pi 3. Okay, so which means what we have here is the intersecting line of the first two planes. The intersecting line of the first two planes, right? This is the intersecting line of the first two planes. It lies on the third plane. In diagram that I drawn for you, I've drawn it like this. Okay, This is the line L. So if this line L lies in the third plane, this is the third plane. Therefore, that tells me that the three planes meet along L. So this in the notes is figure 2, based on page 137. Okay, and that is question 4, part 4. Now into the question 5 of tutorial 1, part 2. Once again, given the three planes, you check if they have any pairs or all the three planes being parallel. If there isn't, we go through the same motion, you know. From the first two planes, we want to actually find the line of intersection between these two planes. You can do this method again. Right, you can do this method again. So what happens is you can obtain the second vector simply by cross product, right, of the two normal vector, which is 5 minus 1 minus 2 cross with minus 2, 1, 3. So let's see, once again, let me make sure that I've copied the question correctly. 5 minus 1 minus 2, 6, minus 2, 1, 3, minus 4, 1, 1, 4, 8, right? So is 5 minus 1 minus 2, minus 2, 1, 3, alright? So let's perform the cross product. This gives you minus 1. 8 minus 4, minus 4. This gives you 3, okay? Let me check that I'm correct. Minus 6, minus 6 plus minus 5, minus 5. Okay, there's something wrong. Let me check again. Minus 3 plus 2 is minus 1. 15 minus 4. Oh gosh. 15 minus 4 is minus 11. Okay, that's why it's good to check, you know. Even I sometimes make mistake, but each time I cross product, I will check, you know. I want to make sure that I'm right. 11 minus 6 minus 5, correct? This is 2, 9, 11, correct? Okay, so that's correct now. So again, to find the first vector, we can arbitrarily put in a 0 for one of the components. So maybe I put 0 as the first component. It really doesn't matter, no? It really doesn't matter, right? Okay. So if 0 is the first component, then got B and C, second the component, my equation now becomes minus B minus 2C equals 6. Then B plus 3C equals to minus 4. So we got to solve for B and C from here. So C is equals to, and B is equals to minus 10. Let's check again. Yeah. Yep, it looks good. So therefore, the equation of my line L is R equals to 0, B is minus 10, 0 minus 10, 2, plus lambda of minus 1, minus 11, 3. Okay. Then the next thing is, we now want to study the relationship between this intersecting line of the first two plane and the third plane. So once again, we check again. Are they parallel? How do we check? Let's check again. I will always write this first though, because if later on the dot product doesn't turn out to be 0, I just cancel all this one as not parallel, you know. I always do this. So because, let's check again. This is 1, 1, 4. dot with -1 minus 11 3. Let's check. This is going to be 0. This is 0. This is 0. Okay, so therefore in this case we know that the line L is parallel to the plane pi 3. And now we are left, as usual, we are left with checking how this intersecting line will interact with the third plane. Just that now, because A is unknown, we can't really check, okay? But the question divides it into two cases, part A and the part B. Okay, let's look at part A first, okay? In part A, it says if A is equals to -9, right? If A is -9, so if A is -9, let me check it. If A is -9, now I take this point, right? I want to check whether or not this point is on the third plane. What I do is I take this point, 0, -10, 2, dot product with 1, 1, 4. Let me check it. If I dot product these two, I get -10 plus 2 is a -2. And this -2 is not equals to -9. So therefore, if A were to be -9, then I know that this line does not lie on the plane pi 3, because this line firstly is parallel, and this point on the line doesn't lie on plane pi 3. So if that's the case, the scenario would be like this now, that the plane pi 3 and the line is like this, the line L. And if that's the case, right? If the intersecting line of the first two planes doesn't meet the third plane at all, we therefore say the three planes don't meet. So in this case, we will say that the three planes don't meet. Therefore, the three planes do not meet. Okay, and also because these three planes are not mutually parallel with each other, and they don't meet. So therefore, in this case, the conclusion therefore will be that the three planes are actually like that. This maybe is plane 1, this plane 2, and this is plane 3. Right? The three planes together forms what is known as the infinite triangular prism. Okay. What if A is equals to -2? If A equals -2, as what we have calculated here, right? If A is equals to -2, then this point on the line L actually, in this case, therefore lies in the third plane, which means the diagram will look like this now. This is the line L, and then the point on the line L is here. And so therefore the line L actually lies in the third plane. So if the line L lies on the third plane, we therefore can conclude that the three planes meet along line L. And in your notes, this will become what? No? Figure 2 in your notes. Figure 2. Right? Okay, that completes our discussion of question 5 of this tutorial.